In class we talked about how thinking of things in terms of waves is often the best way to understand quantum mechanics. And in this case, this is an example of that. To understand the uncertainty principle, it's a lot easier to think about things in terms of waves. So just to review a couple things we talked about in class, if you think about the simplest kind of wave of that you can describe mathematically, it might be a sine function or a cosine function. So it's something that oscillates with a period of some period in time, some amount of time over which it repeats that's consistent forever, and also some amount of distance over which it repeats that's consistent forever. So the distance here, if we think about this graph as being a plot of the wave of the function with respect to x, this is your wavelength lambda, and so this simple sine function repeats over and over and over again forever. So lambda is a certain distance, and then it repeats. We can write an equation for a traveling wave for a sine function, sine of something like kx minus omega t if it's traveling to the right. And then maybe there's some amplitude. So there's our very basic function for a wave, the simplest wave we can imagine. So this thing clearly has a very well-defined lambda, very precise wavelength, but it's spread out over all space. So we talked about how for this kind of a wave we can say that if this function somehow represents position of a particle, the bumpiness of it is everywhere. There's, the amplitude gets big and small and big and small. Technically what we have to do is square this function and to talk about probability. And also we talked about in class how the wave function is really a complex thing. And so really what we want in terms of the simplest possible wave function is like a complex function with a sine and a cosine in it with an I in there, square root of minus 1. When you square that thing, you get a constant for all of x. So this kind of a function, in other words, a quantum mechanical version of it, gives us these bumpiness, these bumpy things kind of go away, but you get, when you square it, a nice straight line that represents one particular value of probability for every value of x. And so there is no place where you're more likely to find the particle than any other place, and that probability is constant for the entire x-axis. So it's a little bit unrealistic. So in that situation we say that the uncertainty in position of the particle is infinite, because the wave function tells us nothing about where it actually is. But yet the uncertainty, if we want to call it the uncertainty in k, is 0. K has a very precise value. 2 pi over lambda is what k is. And k has a precise value. There's no uncertainty in it whatsoever. So, we can think about this in terms of pure mathematics. This is a function that is spread out over all space. So there's infinite uncertainty in terms of, or infinite spreading. Think of delta x as like the spread of the function. That's infinite. Delta k is like the spread of the wavelength, spread of the wave number, and that's 0. There's only one value of the wave number, one value of the wavelength. So if we wanted to figure out a way to represent a particle that we know is more localized, that we know exists over some region of space, so here's our x-axis. If we know the particle is maybe between here and here, then certainly the wave function that represents it has to exist mainly in between these 2 points. It can't be big over in this region, or it can't be big over in this region, because the particle doesn't exist over there. So we might imagine a function that looks something like this. Something like that maybe. Where there's oscillation in it, there's amplitude, size is different in different places, but it's pretty much 0 in these places where we know the particle doesn't exist. It's certainly not 0 in the places where we know the particle does exist. And again, this is just a graph of a function. Technically we'd have to square this thing to get information about probability. Just looking at this function, the fact that it's large at this value of x, for this example I've drawn, says that this point right here is the most likely place we're going to find the particle. But there's large amplitude in other places. Even these places where the function is negative, when we square those places, the whole thing, the square becomes positive. So these are places where there's, decent probability of finding the particle. So, whatever this function is, we'd have to square it to actually get information about probability. But the main point here is that now we have a delta x that's finite. And you can think of delta x as maybe delta x is sort of half the width here of the region that we know the particle is in. So delta x is a finite thing. What happened to delta k? Well, it turns out mathematically that to actually create a function like this, you have to use something called a Fourier transform. And we saw something like this in our first lab, the Mathematica lab that we did, where we added signs together, sine functions together. When we add sine functions together, we get something that kind of looks like this, sort of looks like this, but it's repeated over and over and over again. So let me just draw an example of that. If we just simply add sine functions together, we got something that looked like this, and then it got bigger again, and it got smaller, then bigger, etc. It was like a repetition of these things that we might call packets. So we got this series of packets that repeated forever if we added sines together, sine functions together. So technically what you do in mathematics is you integrate. You change your addition into an integration, and you do an integral of sine functions with different amplitudes, and you add them together. And when you do that correctly, these little packets kind of die away out here, and they die away out here, and you're only left with one remaining wave packet. So you get something, doing this Fourier transform, which involves an integral rather than a summation, you get a wave function, or just a function, that exists in a finite region of space, and all the other stuff beyond this region is very, very small. It goes to zero. And that's what we're looking for. That's exactly what we want when we want to represent a particle that's within a certain region of space. So when you do that mathematically, what you find is that because you're adding together sines or cosines, whatever you want to call it, the wavelengths are different for each sine function. The lambdas are different. And therefore the k values are different. You're adding up a bunch of functions that have different k values. And so the uncertainty in k in the overall function is now some non-zero number because there isn't a well-defined wavelength. This distance from maximum to maximum is not necessarily the same. Say from there to there versus from there to there. That distance is not necessarily constant. And so there's some uncertainty. So you have now some delta k. So we had delta x is not equal to infinity now. We also have that delta k is not equal to 0. And so you get this sort of switching. As one thing goes up, the other thing goes down. As delta x goes down, from having a single sine function to having a bunch of sine functions, delta x goes down. Delta k then correspondingly goes up. The uncertainty in wave number, the uncertainty in wavelength increases. And this is just a basic fundamental property of waves, and adding them together to form a wave that's more localized, that represents a particle that's in a definite location. So when we translate this, when we do this more precisely mathematically, we find that the product, delta k, we find that the product delta k times delta x, if we just multiply these uncertainties together and define them in a more precise mathematical way, just purely mathematically, we find that this is greater than or equal to 1/2. Just mathematics, that's all it is, no quantum physics whatsoever. But now we think, okay, quantum mechanically, what is delta k? Well, delta k is, if we think about what k is 2 pi over lambda. So here's 2 pi over lambda. And if we think about what lambda is h divided by momentum. So k is the same as 2 pi over lambda, or 2 pi over h divided by p. And then that we can write that as, the p comes up, and the 2 pi divided by h bar, or divided by h is h bar, or 1 over h bar. This is then p divided by h bar. So we can write k as p divided by h bar. So delta k then is delta p divided by h bar. So we have this, that delta p divided by h bar, not a very good h, times delta x is greater than or equal to a half. And then if we move the h bar over, we get our delta p times delta x is greater than or equal to a half, and that's our uncertainty principle. And technically we should be writing, this is the x component of momentum is really what we're talking about. In this case we're just talking about one-dimensional motion along the x-axis. So our result then is that delta p with an x subscript, so the uncertainty momentum in the x direction times the uncertainty in position in the x direction, is always going to be greater than or equal to, greater than or equal to, let me erase that, something strange there, it's always going to be greater than or equal to h bar over 2. Now this relationship applies to other directions as well. If we thought about particles moving in the y direction, we could measure the position in the y direction, and we could measure the momentum in the y direction, and we'd get the same relationship. We'd have a delta p y delta x, or delta y, is greater than or equal to h bar over 2, as well as z, delta p z times delta z is greater than or equal to h bar over 2. And so when you make measurements of momentum and position in one particular direction, those two measurements are complementary. They don't sort of, in a sense, like each other. As if the certainty of one is better, the certainty of the other is worse. You know, the uncertainties. If the uncertainty in one is small, meaning we know it very well, then the uncertainty in the other one is large, meaning we don't know it as well. So we'll do an example of this, and we've done some examples already in class, but one other thing we'll look at here really quick is the fact that this function, these wave functions, are functions not only of position, but they're also functions of time. So we can do the same kind of analysis that we've just done, but instead of plotting this thing at a single point in time as a function of x, like we've done here and here, these are all functions at a particular instant in time. And we're talking about measuring momentum and position at a particular instant in time. We can do this sort of the other way and think about plotting this function at a particular point in space. Imagine that, put a value of x in here, so imagine that you're at a point in space and you're letting the wave pass you by. You're looking at this wave as time goes on. So we're going to plot this thing as a function of time. So we'll do that on the next page, and that'll give us another uncertainty principle that has to do with time. So here's our function again. We have sine. We were looking at just a basic sine function, so sine of kx minus omega t. And what we want to do now is, instead of graphing this thing as a function of x at one particular moment in time, let's make a graph of this thing as a function of time at one particular value of x. And again, it looks just like a sine function. I guess technically, if we're going to put in, say, x equals 0 here, then we have sine of negative omega t, and so, you know, technically it would look like an upside down sine function. So we can draw that. It's not a big deal. It doesn't make a big difference. Again, the point is that with a sine function, it's a function that oscillates up and down forever. It has the same distance between peaks. This distance now between peaks is not a wavelength in space, but it's like a wavelength in time. It's the period. So the distance from there to there is your period t, the amount of time that it takes for one wavelength to pass by. So t is your period. T is 1 over the frequency, 1 over f, the frequency. So t is sort of analogous to lambda. And so in thinking about particles, we might want to think about a particle existing, or some kind of a state of a system. Sometimes we're going to talk about wave functions that represent like states of a system, literally a state of existence of an atom, for example. We might talk about a hydrogen atom. If we give it some extra energy, we could say that it has some extra energy. It's sort of holding on to that extra energy for some amount of time. It's in that state of extra energy for some amount of time. So what this wave function represents, what the sine function represents, is like a particle that is in a particular state for all time. So this particle I mean, this function oscillates for all time. It keeps going. This is a time axis. Time can go to infinity, and this function still oscillates because of the fact that it's just a sine function. So this kind of represents a particle or some state of existence that always exists. There's infinite time. All right. So in a sense, in the same sense as we talked about with x, the uncertainty in x being infinite because the particle or the wave was spread out over the entire x-axis. In the same sense here, this wave is spread out over the entire time axis. And so we don't have any certainty as sort of, in a sense, when the particle exists or when the state exists. It exists for all time, kind of like in the previous example with the sine function spread out over the entire x-axis. In a sense, the wave is everywhere on the x-axis, so in a sense, the particle is sort of everywhere on the x-axis. Again, it's not good to really think about particles per se, but always think about waves. The wave is spread out over all of the x-axis. So the position of the thing that the wave represents, the particle, is totally uncertain. In this case, the function is spread out over all time, and so the time at which the particle exists, or the time at which the thing, the state, whatever it is that this function represents, exists, is totally uncertain. The function is spread out over all time. So we can write down that delta t in this case is infinite. The uncertainty in time is infinite. The function has infinite, it's spread out over the entire time axis. We have no idea when, in a sense, whatever it represents exists. So is there an uncertainty in something that's zero? Well, yeah, we can talk about the uncertainty in the period. The uncertainty in the period or the uncertainty in the frequency. And we'll actually talk about frequency. So, frequency, just kind of reversing this equation, is 1 over period. Kind of like wave number was something over lambda, 2 pi over lambda. This is frequency, f, was 1 over period. Omega, then, omega is 2 pi f. The angular frequency is 2 pi f. So that is 2 pi over the period. So this is very much analogous to k, which was 2 pi over lambda. And so we see that because this function has a very well-defined period, a very well-defined time over which it repeats, the uncertainty in omega is 0. So this is very much analogous to the last situation where we had delta x being infinite and delta k being 0. Here we have delta t being infinite and delta omega being 0. And now you think, okay, let's think about how we represent something that's more realistic. How do we represent a function that represents a particle or an object or a state that exists for a finite time? And so if we want to imagine, again, drawing a time axis and try to come up with a function that represents some state or some particle that exists over a finite time, from this time to this time. Again, that might look like something like this that oscillates within this region. And it could look complicated, who knows. But the point is that it's mainly, wherever it's large, it's large in here somewhere. Whatever it looks like, this is where it's sort of large in a sense, and it's very small beyond these times. In other words, this function represents something that exists from this time to this time. Maybe a particle is created at this time, and then it decays at this time, and it turns into something else. All right. So this is a better function that might represent something more realistic, something that doesn't last forever, something that exists for only a finite amount of time, some state of existence of an atom, for example. An excited state of an atom doesn't last forever. So the wave function that represents it is going to be something that doesn't extend over all time. So, again, we'd use Fourier transforms to get this. We'd add up a bunch of sine functions, sines or cosines, adding up a bunch of sine functions like this, all with different frequencies now, would give us something that looks like this. Technically, when we algebraically add sine functions together, again, we're going to get something like we had before, where we get these little wave packets that repeat themselves, like this. And they just repeat and repeat and repeat because the sine function repeats and repeats and repeats. So what we do is we don't do an algebraic sum, we do an integral, and we add things together with add a bunch of sine functions together with different frequencies, but we do an integral rather than a sum. And what that does is it gives us back just one single packet of wave over one single region of time. These other guys kind of die away. So you get something like this when you do the actual integration. And again, when you do that and you analyze the properties of the spreading of this packet, and now we can sort of define half of this spreading as being your, in this case it's the time again, you could call it your delta t. And delta t now is not equal to infinity. This thing represents a particle or a state of some sort that exists over a finite time. And you can show again mathematically that to do this, to create this function that exists over a finite time, you have to add up a bunch of waves that have different frequencies. So you would have then that delta omega is not equal to 0. It's gotten larger because you've added more waves together that have different frequencies. In other words, the distance in time between this peak and this peak is not the same as the distance in time between this peak and this peak. The period isn't well defined anymore, so the frequency is not well defined. And again, in analyzing this mathematically, you can show that delta omega, if you define these things carefully, precisely, rigorously, we're not doing that here, but if you define these things mathematically in terms of these Fourier transforms and properties of them, you define sort of the width of the function in terms of frequency, the width of the function in terms of time, sort of roughly like half of the width of the function here, roughly. You find that this product, delta omega times delta t, is always greater than or equal to 1/2. And this is purely mathematics, no quantum physics whatsoever here. But then you say, okay, well, what about quantum physics? Well, what is omega related to for a particle, for a thing, for a state of existence of something like an atom or something? Well, we talked about how we define energy as being either hf, h times the frequency. That's how we define the frequency of something, is we say that its energy is h times its frequency. And this is perfect for light. It works perfectly for light, but we assume that it works for particles, other things we think of as particles. But again, remember that everything's a wave. It's better to think about everything in terms of waves. So we define the energy as h times f, or that's the same as h bar times omega. So solving for omega, we get energy over h bar. And so delta omega is delta energy divided by h bar. So we can write the uncertainty principle as delta E over h bar times delta t greater than or equal to 1/2. And then you bring the h bar over and you find our energy time uncertainty principle. The uncertainty and energy of a state, of an object, of a particle, or whatever you want to call it, times the uncertainty in the time. And by that we mean how much time do we have, in a sense, to make this measurement of energy? How much time does this thing exist for? Roughly. There's more precise ways of defining these uncertainties. But roughly, how much time does this thing exist for is your delta t. Or maybe 1/2 of that is your delta t. And then what is the uncertainty and energy? The product of those two things is limited. It has to be greater than or equal to h bar over 2. So we'll do an example or two of this, and we've done some examples of the position, momentum, uncertainty principle. But the energy time uncertainty principle is another one that's very useful. Again, these don't give you ways of calculating precise things, but they give you ideas of how small things could possibly be, and the fact that there are many things that we think classically could be zero, like speed, energy, and such. We'll find that quantum mechanically they can't be zero. And it's all based on the uncertainty principle and the fact that everything is really a wave at the